Hello, we are looking at finishing up this mod, and here are the formulas that came out to play, and we are actually answering the review questions from the book. And they are at the end of mod 9, and the first one, would you read it, MD, and tell me your answer?
An object's velocity vector points 45 degrees northeast. What is the direction of its momentum vector? 45 degrees northeast.
Right. Alright, that's one thing we could do for the video land, is maybe just have them watch the questions. It's kind of hard for them to hear them that fast, you know, if they don't have this book. Alright, video land, here's what we're doing. Could you just shine it on that? I guess you can get it down that low. I mean, from the stand, so you don't have to.
Okay.
Is it on there?
Yeah, just leave it on there
Yeah.
the whole time.
While we're talking, we'll eventually be finished. And if I put something on the board, you'll have to switch it back up. Is that good?
I think they can
Alright,
probably
we just
read
did
it.
number 1, and we said the answer was 45 degrees
The
northeast.
final and last call for Chick-fil-A for today. If you're ordering Chick-fil-A from us, please bring it to the office immediately. Thank you.
Alright, Zach, what were the 2 or 3 or 4 or 1 units which are legit for momentum?
I think it was the two middle ones.
Right, right.
Minutes.
Because what kind of units are you looking for?
You're looking for kilogram over meter per second.
And so why did number 3?
Because we have squared. Wait, what?
Why is number 3
This one
good?
and this one.
Because it's feet per kilometer hours. It's in the
This is not.
American. That's not right.
I call it American. There doesn't the non-metric system.
Non-metric system.
Right.
Only
so
America.
We still have a unit for mass, which is what, Zach?
Feet. Oh wait, yeah. Wait, slugs. Sorry.
Slugs. And then the
you still
unit
have
for velocity is
hours.
what per what? A unit for velocity.
Feet per hour.
All right, feet per hour and slugs, so it works.
Yep.
All right, MK. Under what conditions? Read that one.
Under what conditions can a compact car have the same momentum as a larger, heavier car?
All right, and how could that happen?
If the smaller car is going faster than the
Right.
larger car.
There's 2 parts to momentum. So if they're saying that there's a large car, a heavier car, so the only way they can have the same product, m times v, is one, the smaller one is going faster.
Number 4.
Did you get that? All right, Alex, read number 4.
The golf ball and a lump of soft clay are both thrown at a wall. They each have the same mass and are thrown at the same velocity, and they each stop dead when they hit the wall. On which object does the wall exert the most impulse?
Okay.
The lump of clay.
You know, I think I led you to that, didn't I? I was wrong. All right, so anyone get a different answer? I kind of led you to that. When anyone asked yesterday, I kind of led you to that answer. So on number 4, we're dealing with this, the fat equation. And so it turns out that it says that they have the same mass and they have the same velocity and they each stop dead. So that means they both have the same change in momentum. Agreed? Because they have the same mass and the same velocity. So if that's true, the wall, when it hits the wall and comes to a dead stop, is going to go from whatever it started with to 0 in both cases. So therefore, they're going to have, the wall is going to exert the same impulse on each. Now these parts are going to be different, and I was kind of pushing you in that direction. One of them's going to have a small force and a large time, the other's going to have a large time and a small force. But that's not what's asked for in this question. It's asking which one does the wall exert the most impulse. Impulse is this, which equals that, and this went from the same number to 0 in both cases, so we have to say that the impulse was the same on each. So I kind of led. Yep. I kind of led you in the wrong direction there.
Does that apply to the next one then?
No, the next one we kind of have to break up into force and time. So, read that one.
In the situation from question number 4, of which object does the wall exert the most force?
All right, so now we're talking, I was leading you in the right direction yesterday for that. So do you recall what I said or led you toward yesterday?
Well, isn't it the golf ball?
It has more force?
Yeah.
Right, and why is that?
I forget what you
It has something to do with the amount of time that the objects have in contact with the walls.
yeah.
So which one is gonna have larger time?
Clay.
The clay, because it's gooey and ooey and it sticks a fraction of a second longer, and the ball will just touch it quickly. So the ball, this will be a low number and this will be a high number because they have to equal the same number over here. So for the clay, this will be a large number and this will be a small number. So the answer is the golf ball. All right, MD, read the next one.
Okay, hold on. I gotta put it on for them. A cat and mouse are both running with equal kinetic energy. Do they necessarily have the same momentum? Why or why not?
All right.
I put yes because kinetic energy uses mass and velocity, and that's the same thing that momentum uses.
All right.
So
Let's
if they
do
have the
what I
same-
did, I think we can verify what you said or not verify what you said by looking at an example. So they're saying what two things are equal? Kinetic?
Kinetic energy and then
All right, kinetic
momentum.
energy of the mouse is kinetic energy of the, what was it, cat?
Mm-hmm.
So we have 1/2 mv squared of the mouse is equal, they claim that, the cat. All right, so let's make up some numbers, MD, and see. And we'll take the numbers, we can make them up as long as they're equal, and then check their momentums. Then we'll come down here and check MV of the mouse and MV of the cat. So pick a number for the mass of the mouse. Pick a nice, easy number.
2.
All right. So you're going to put in a 2 for the mass of the mouse, and take an easy number for velocity.
4.
All right. So this is like meters per second, and this
Yeah.
is kilograms. But we're not going to mess with that. All right. Now you've
Don't
got to
forget the
be
square.
realistic. You want something larger for the cat, because a cat is larger, hopefully, than the mouse. But these numbers have to be equal. So we got to think of a number, or we can change this to another 2 numbers that work. So what could we put in for mass of the cat that would make sense if the mass of the mouse is 2? Just make up something. 4? Is that what you said?
Yeah.
All right. So is there a number? So this side is what? 1/2 of 2 is 1 times. This side is
Well, that's
4.
squared.
Or the
4 is
yeah,
squared,
you're right,
so that's-
you're right. So we got 1/2. We got 16 over
So
here.
it would have to be
So what?
2.
2, would that work?
2 times.
squared?
Wait, no, it would have to be 2, 4 times. No,
This
that
is
wouldn't work.
1/2. Okay, not 2. Is there a number? 1/2 of 2 is 1. 1 times 4 squared. This has to equal 16. So we have 1/2 of 4
That's 2.
is 2, and we need this what?
So that
the
needs to
square
be
root of
8. Square root of 8.
I was hoping for better numbers than that. But,
Whoops.
all right, it'll work, right? All right, so do both of these equal 16?
Yes.
All right, by example, we gave the mass of the cat, mass of the mouse 2, the mass of the cat 4, because the cat's heavier. And then we made up a velocity of the mouse to be 4, which is squared. And we knew these two numbers were equal because they told us their kinetic energies were equal. So we knew this had to equal that. So the only way we would do that is we put a square root of 8 into that. So we're just making an example. If it works in one example, it doesn't mean it works in others. But if it doesn't work in one example, we can. It said, how they word it. It said, do they necessarily have the same momentum? So if we can find one example that doesn't, then we can say no. So, all right. So are these? We're going to grab the mass of the mouse and put it down here,
Wait,
and the
I don't
mass,
think that works.
the velocity of the mouse, and put it down here. Is it going to be equal? Take the mass of the cat, and we got 4, and square root of 8 for the velocity. Is 2 times 4 equal 4 times square root of 8?
No.
No? Okay. All right. So by example, we can check it out. And theory-wise, when is the only numbers that I think the only numbers where eventually this number has to equal this number. I can cross the 1/2 out because they're on both sides, but this number has to equal this number. And what number for velocity, I can cross these out. What number could I put in for v, that when I square it, I get v? Zach, what number could I put in there for velocity? 5 minutes? Are you kidding me? Oh, this is insane. Zach,
Which one's last?
Yeah.
Please tell me.
what number could I put in here and square it and get that number? There is a number that
The
works.
square root of v.
Of what?
The square root of v.
Square root of v. So if I put the square root of v in here,
Oh, 1.
yeah, 1 works. V equals 1 and another number.
0.
Right, and those are the only two where it would work, but it doesn't necessarily work, as our example showed. So all that who struck to say on number 6, no. And why? Because we tried an example and it didn't work. We set two kinetic energies equal and we tried their momentums and they didn't equal each other. All right, let's see if we can finish this review. All right, MK, read 7.
Under what conditions is momentum conserved?
And what is that?
When there's no outside force acting on it.
Right. Okay, so the sum of the forces acting on the system are 0. There are no net forces.